Awesome, we're live. Hi, everyone. Welcome back to the MLSys seminar. Hope everyone had a great Thanksgiving. Today, we're super excited to welcome Tianqi Chen, who's a professor at CMU in machine learning systems. He's built several widely used systems that automate various aspects of the machine learning pipeline, such as compilation for different types of heterogeneous devices and parallelization, amongst others. One of the particular systems he's well known for is called TVM, and he's going to talk about some of the various systems that he's been building at CMU in this talk today. He's also the Chief Technologist of OctoML, and prior to his professorship at CMU, he was a PhD student at University of Washington. With that, Tianqi, take it away. Thanks.
Thank you. Let's see. Can we see the screen?
Looks good.
Awesome. Yeah. So thanks for the introduction. Happy to be here. So today I want to give a talk about some of the recent works we do on bringing foundational models, consumer devices with ML compilation, which is a pretty exciting topic. So to begin with, I would like to start to recap about the history of machine learning revolutions. And as we know, the ML and the overall machine learning have become critical in some of our modern applications. And overall, over the past 20 years, we have seen several breakthrough points that enable some of the key capabilities. The first breakthrough point is, I would say, the availability of bigger data. And some of the models, including recommender assistance and data analytical model that works on tabular data. Those models helps you to do ranking recommendations, give predictions, and enables modern recommender assistance and advertising system and so on. And they are being powered by some of the machine learning systems like XGBoost that we build, Apache Spark and GraphLab, and other systems that really enables the data analytical capabilities of machine learning. If we switch forward, we arrive at the time of the era of deep learning, right? Where in about 2013, we start to see strong ability of doing pattern recognitions, be able to see through images and classify them and create bounding boxes around them. And there are useful machine learning systems being built for those capabilities as well, such as TensorFlow and PyTorch. And more recently, we are at an area of generative AI, right? We are starting to see these models being able to not only recognize patterns, but be able to have open-ended conversations of things. And I would argue that in this case, machine learning system would even play a more important central role, just as of the last two revolutions. So today's talk, we are going to focus on question about how we can enable systems for some of our generative AI tasks. These models are really powerful. Here's the model that I think is the Llama 2 7 billion model. You ask it to introduce Pittsburgh, and you can, do open-ended question answering, which is kind of surprising. Even about, if 2 years ago somebody asked me whether or not a model can do that, I would say maybe it's not, yet ready, right? We are still at a pattern recognition age, but now, we are at something that's much more fun. But they also create very great amount of challenges on deploying those models and optimizing them. First of all, these models have large amount of memory consumption requirement. Even if you start to look at the 17 billion model, if you do it in 4 floating points, it's going to fit into 300 gigabytes of VRAM, and most of the GPUs don't have that amount of VRAM. We're also at a post-Moore era. That means that you can no longer just hope the compute is going to continue improve, right? You kind of need to rely on specialized compute, like specialized compute accelerations. And that means that we will need to build specialized software for supporting those compute, and system support can become a bottleneck. There are also challenges on how you go and integrate different components, such as making the application to talk, compose, and coordinate multiple model and system components. And finally, because of the need to always push the frontier, there's always new demand on creating new modeling approaches and supporting hardware variants and co-design among them. So how do we do that? And one of the goals that I would like to mention is that we are still at the dawn of the generative AI age, right? And today, if you start looking at the Gen AI, most of the paradigms people run is you start to try to put something on the cloud that works, then you have a backend that works for certain kind of hardware, and you start to talk to the models on the cloud. But just like when computer first get out, people say that there are 5 computers are be sufficient for supporting the entire nation's needs, right? But now we're at a personal computer area. How can we enable personal AIs that just like personal computers? And in this case, I would argue that you would need this model to run a much more variety of devices out there, and that including those consumer devices like your mobile phones, your handheld devices, game consoles, and so on. But this will create a much bigger challenge in terms of how do you build software stack that goes across in a more efficient manner. Most of our machine learning engineering approach today tries to create specialized stacks. You will go and try to build specialized optimizations for each of the backend. They can be labor intensive. Even some of the specialized framework, Llama, CPP, have to go and write specialized kernels for each kind of new hardware backend over there. So one of the questions that we ask over the past few years, how we can automate this process a bit more so that you will be able to build portable solutions across wider variety of environments. And that comes to this approach called ML compilation. The goal here is you want to import a model into what we call common program abstractions. You try to perform some composable optimizations on them, and you try to generate code for the particular kind of hardware backend you are interested in with the universal deployment runtime. So the goal here is you really want to not build specialized solutions for each of them, but trying to build more reusable optimizations in there. And we started working on this area about, I think, 5 years ago. And I think more recently, you also start to see ML compilation getting tractions in frameworks like PyTorch Compile and the XLA as well. But in general, the theme of the talk is how we can leverage ML compilation, right, to really deploy the generative AI models more universally. So in order to do that, a great majority of the talk, I'm going to focus on some of the challenges and common approaches of doing ML compilation. So in general, if you have a high-level machine learning model, what ML compilation tries to do is you want to try to encapsulate your computations in what we call the program abstraction that represents the programs. And then usually there are different levels of program abstraction they can use to represent those programs. You can, for example, use computational graphs to represent the high-level computations and dependencies. And then we have tensor programs that represent how you have loop nests and you go and optimize those loop nests. There are also library runtimes that are built by vendors and engineers to accelerate key operators of interest. And finally, there are hardware primitives out there. Most of the machine learning frameworks and compilation frameworks as well try to build this solution in what we call a layered approach, where you have one layer that optimizes for computational graph, another layer that builds library runtimes and lays on top of the hardware primitives, and they present a closed box to the AI applications. However, the challenge here is actually in a lot of cases, we do want to consider all those perspectives jointly to optimize your applications. So we have worked on this area for quite a few years, and one thing we find is that the biggest challenge is not only about building a solution that works for the current need, but continuously improve your solution as the demand of machine learning modeling changes, like different variants of language models, different variants of the positional encoding and diffusion models, as well as the different variants of engineering approaches changes, where there are things like trying to be able to build different variants of attention mechanisms, different layout patterns. If you want to distribute things, how to shard your parameter, and how do you dispatch to quantized kernels, for example. And when we make innovations on these areas, they are usually intertwined with the other parts. And the question is how we can continuously build and improve the solution while making innovations on some of the part of the overall compilation pipeline. So over the past few years, we have been building this overall approach called TVM Unity. And the goal here is we want to be able to have a way for us to continuously improve the ML compilation pipeline in a more friendly approach that's also Python first. I would like to unpack the approach here in several elements. The first thing is that we do need something that captures the computation of the ML programs in order for us to deploy them onto environments like mobile devices, browsers, and so on. So in here, this central element is called IR module. And the IR module is a collection of functions that correspond to model components. For example, if you're looking at Things like stable diffusion models might contain a clip component, a scheduler that do updates, a UNet and VAE component. And actually, in our framework, each of the function can be represented what we call an embedded in a Python AST style DSO that represents the set of tensor computation we do. And we will be able to also interact with it in the Python environment. For a given IR module as a centralized component, we'll be able to start to build development flows of ingesting machine learning models as well as optimizing them in the Python first approach. So first of all, we will be able to ingest the models from existing front end, or you will be able to construct them on a fly using some of the construction APIs. We will be able to take those models and transform them and trying to interact with them in different ways. Like I can take existing loop nest that is playing vanilla loop, and then we can transform them to map them onto GPUs so that you will be able to run some of the things on GPU. We can compose certain transformation together of, for example, doing operator fusions and so on. And finally, you can deploy it onto the environment of interest. So everything, all the optimization are centered around this IR module API that allows you to be able to do program transformations. And there are different kinds of them. You can do high-level optimizations as well as low-level mappings onto the existing low-level model libraries. For a given IR module, one thing we can do is we will be able to go and build it for a given target, and you will be able to take that and have a runnable module on the environment you are interested in. So there's a very simple one-to-one mapping. So for every IR module on the left-hand side, when you build it, you're going to get what we call a runnable module. In this case, there's a virtual machine that executes that runnable modules. And you will be able to, get a runnable functions on a target environment. For example, you will be able to have a VAE function on the left-hand side. It's going to correspond to a VAE function on C++ that interact with some of the ND-array APIs that you had. Or, in Python, it's just a Python function that is going to interact with the input data and parameters and output related ND-arrays. We also have other runtimes like JavaScript, Java, and other environments so that, the user will be able to deploy the machine learning models on the platform that they're interested in a bit more unified fashion. So overall, the goal here is to build a productive framework so that we can take in high-level machine learning models, run the transformations on the IR module itself to bringing in different optimizations and improve this overall transformation pipeline so that, we will be able to, for example, dispatch to new libraries if necessary, and replace with new memory planning algorithms so that we get more efficient memory usage across all the board. And it's a continuous improvement process. So the idea is that we will be able to get a ML compilation pipeline on the left-hand side that's out of box. But as new hardware backend settings and library comes, we are going to improve that pipeline in a more transparent fashion using the overall Python first compilation flow. Okay. So I've talked about the high-level idea of the TVM Unity. I'm going to dive a bit deeper onto some of the key elements of the abstraction. Then I'm going to come back to possible applications of the approach. So I'm going to dive into 3 elements that enables TVM Unity to be able to generate code efficiently for some of the Gen AI workloads. The first is first-class symbolic shape support. So as we know that if we're looking at machine learning models, a lot of machine learning models now come with dynamic shapes, right? You might want to have different batch size, or you might want to be able to support different sequence lengths in the language models. In those cases, the shape of the input tensor is no longer static. And in this case, we want to be able to bring in first-class symbolic shape support. Normally, if you look at machine learning, most of the machine learning compilation approaches, a lot of cases, people use what we call any shape dimension. That means that, if certain dimensions are unknown, you're going to have a question mark on the corresponding dynamic shapes, which means that, this is the unknown shape. And then we're going to build a runtime function that dispatches onto the existing, on a possible implementation in there. Symbolic shape, on the other hand, try to check the dependencies among those unknowns. For example, we will be able to know that the first input is n by 2 by 2. If you reshape it, it becomes n by 4. And if you flatten it, it becomes n times 4. And you will be able to know the relations, right? So we'll know that, for example, the total size and total number of elements of LV1 is n times 4, which is the same as the total number of elements in X. While in the any shape case, it's just a question mark. So you are not able to reason about relations between them, okay? And the ability to be able to have this symbolic shift support allows us to do many more optimizations that otherwise are not possible globally. For example, we will be able to plan memories so that, even though there's a dynamic shape, we can try to allocate all the static memory ahead of time if you know the upper bound of some symbolic variables. We can also perform, more advanced optimizations like dynamic shape-aware fusions and layout rewriting. So that's the first element of dynamic shape. The second element is about, composable tensor program optimizations. And that comes into the hardware trend where, we start to see a bit more tensor computing in our hardware, where normally you only need to care about scale operations, but now you need to start looking into, tensor computations. In order to do that, we want to be able to have, high-level loop nest, as well as multi-dimensional tensorizing instructions and load and store and matrix multiplications. So there are different ways to represent these programs. You can either do it in what we call bottom-up, top-down way. But the key idea here is that we want to be able to try to encapsulate these tensorized computations in what we call isolated components. So in this particular case, we are going to introduce a key construction called a block that allows us to be able to take in the computation loop nest, but also allow us to isolate a subset of block that correspond to tensorized computation, like matrix multiplication and multi-dimensional load. Besides that, the key idea is the block will be able to isolate the dependencies within the block and outside the block. So we'll be able to perform transformations by just looking at the block signature. And it can also be multiple level of blocks so that we'll be able to compose low-level constructions and to form a higher level blocks in there. So with the block, one thing we can do is we can start to manipulate the loops by looking at block dependencies and transform them to more efficient programs. And this gives us the ability to be able to explore the space of possible program transformations and get optimized version of our programs efficiently. We can also start looking at loops and try to take a subset of loop and introduce a new block. And finally, we can do a process called tensorization, which is a process to map a subset of the loop nest, block loop nest onto the bulk matrix multiplication or other instructions available in there. So we've talked about tensor IR, and I also want to talk about how this block abstraction feed back onto the overall unity abstraction. So the goal here is we want to be able to have the IR module that contains computational graph node that calls onto those loop nesting functions. And also be able to represent the loop nesting function abstraction in the same program. So by doing that, we will be able to write optimization passes that take the existing function, analyze loop patterns, and rewrites it and updates the original function. That gives us ability to be able to modularize and optimize a particular part of the computations. Okay, so that's the second element. The third element I want to talk about is the unifying compilation library. So if you start to optimize low-level machine learning computation before, you'll find that usually there are two approaches nowadays. You can either have a library-driven approach that focuses on performance, but it's very engineering intensive because you need to go and optimize for kernels for certain operators. And you have a compilation-driven approach that try to generate code that's a bit more generic, but sometimes it's hard to apply critical optimizations for all the possible cases. So the sweet spot usually is in between, but usually most of frameworks are structured in one way or another. So it's really hard to try to combine both two approaches. So in this case, in the unity abstraction, we'll be able to have the code that not only tries to run into that not only try to call into the tensor functions, but it can also directly call into libraries that are registered in the runtime. For example, we could directly call into what we call cutlass function, and which is getting registered in the C++ runtime, so that it allows you to be able to directly integrate library calls onto your low-level compilation and mix that with some of the code gen approach. So usually what we can do is we can take existing operators and try to map that onto some of the offloading paths that runs on the target environments. And the goal here is not only you can do that through library offloading, but in other cases, you can also pass the rest of the component onto native compilation in a very natural manner, okay? So we've talked about the three elements, the high-level flow of the overall TVM Unity compilations. I would like to mention, what does it mean in action? So again, the goal is we want to build for input model. You can import it onto our module, perform modular transformations on that module, and then finally you build and try to deploy it universally onto an environment you are interested in. And in a common practice, what we do is we try to build specific domain-specific pipelines. So for example, for certain models like language models, we can try to build a specific kind of optimization pipeline and transformation pipeline so that you can target that particular kind of modeling. And in order to do that, there's also a question about how you can continuously improve the performance as you start to look at new hardware backend as well as the model variants. So typically what you have is you will have an out-of-box pipeline that allows you to have a pre-built set of transformations that transform an IR module to make it more efficient. But then a common question that we face is that we want to continuously improve that. So we sometimes, for example, maybe we want to have a better attention implementation. And in this case, we want to be able to create a new path that dispatches certain operators to a new attention implementation, but still fall back to some of the existing compilation pipelines. So, it handles the rest of the code gen for us. Or sometimes maybe you want to try a new fusion patterns. In this case, you can take an existing module, insert that customized fusion patterns, and then follow up with the rest of the fusion path that enables the rest of the optimization. So the goal here is we will be able to quickly customize the new ideas, like trying out a new attention operator, while trying to validate that together with the rest of the flow, right? So that, for example, if you already have a robust flow that deployed to Android, and you just want to try to test out one special variant of attention on for a particular, maybe Qualcomm GPU backend, you can try to do that and quickly validate the performance. And then, depending on whether or not you want to generalize it, you can directly deploy it productive if necessary, but you can also summarize the lessons and try to build a more generic compilation flow if necessary, okay? So we've talked about general approaches. I want to switch back here and talk about specific applications of that particular approach and try to apply it onto bringing in generative AI models onto, like we said, a broader set of devices, especially consumer devices. And there are, a lot of opportunities on enabling that. So the challenge of deploying these models onto consumer hardware is that there are great diversities of hardware and software stack out there. So even if you just count them on GPU runtime you can have, there are at least 9 of them. And I guess it's the growing number that you can start to count on possible ways to support a consumer device out there. So what can we do? This is where really, ML compilation can help. And we can structure a specific language model compilation pipeline that follows the overall pattern of the overall ML compilation. So the idea is that we will take the models like Llama 2 and Wizard and Mistral models, you import them, try to construct them in the form of IR module. You perform targeted optimizations using things like dynamic shift memory planning, low bit quantization, fusion hardware optimizations, and we can generate the code that runs on the possible target platforms through a universal deployment runtime. Okay. So we have applied these approaches and started to build some of the project, which is still ongoing. But we also have some exciting preliminary results on enabling those language models on different kind of environments. For example, we have an MLC chat API that allows us to be able to compile the Llama models and the open model variants onto different environments that runs on both Windows, Linux, and Mac, right? So, and they also use different GPU backend. Like this is a case that runs on Mac, they use Metal backend, while on Windows, you will need to use Vulkan that supports a broader set of the environments out there. And actually, generalized to 17 billion if you have a largest, M2 Ultra or M2 Max GPU in your machine. Another fun thing that we did is actually, we can use the same approach and compile onto mobile devices. In this case, if you go to the App Store and search for MLC Chat app, you will be able to download MLC chat app that allows you to chat with, I think this is a Llama 2 7 billion model quantized to 3-bit, which is pretty cool. And you can still, try to fit these models on the 4 gigabytes of budget. It's a bit power draining for them. So it's, I think, for the 7 billion model, it's still a bit of pressuring the demand. But for iPad or, if you just run on iPad or run on your actually MacBook as an iPad app, actually it's totally fine app that you can go and try it out. And there are also smaller models like RAG pajama models that are actually pretty decent and actually cause less overheating issues. The same solution also support for Android. In this case, Android will need OpenCL backend, which is different from the Metal backend. Right? So traditionally, if you want to go and support models for different GPU backend, you will need to go and write specific kernels for each of them. But in this case, we are trying to leverage a code generation approach that generates most of our code so that it's more generally retargetable in some sense, but you still need to perform some specific optimization for the target backend, but a lot more code can be reused across the stack. One thing that we did in the summer is that we try to start to building support for GPUs, AMD GPUs. So in this case, on the single batch inference performance, we are finding that actually we can get pretty decent performance that are comparable to some of NVIDIA variant tiles here. And again, this is also something that we found interesting is the time cost that we spend on optimizing certain kind of hardware backend. When we start to set goals on doing it, it's greatly reduced, so that we know in this case we spend about 1 day effort after connecting to ROCm stack and about a week to go and optimize some of the performance overall. Another fun thing we can do is we can try to scale down the models and think about how cheap you can go. So this is a case where we are running, I think this is a Llama 2 model on $100 Orange Pi. So this is a single board computer that costs you about $100 and come with an ARM GPU. And for Llama 2 7 billion, I think it takes you about 2 tokens or 3 tokens per second. Not very fast. I think just usable, right? For RAG pajama models, the 3 billion versions it gives you about 5 tokens per second, which is pretty usable as of now. If you want to try one demos today, I would recommend trying this one because it's the easiest. So if you have a laptop, what you can do is you can just go to this website called webllm.mlc.ai, and there's a chat demo. You do need a Chrome browser and a laptop with a with a GPU. And what happens is that this is a demo that runs this language model directly on your browser using your local GPU. So in here, what we do is we compile the code into WebAssembly and Web GPU that leverages the local GPUs that you have in your local environment. And the first time when you load the demo, it will just try to go and download the weight and cache it in a browser cache. So and the second time when you run it, actually it's going to load very fast, and you will be able to chat with the model that you're interested in. It's also available as an NPM package. So the default UI is certainly not the prettiest, right? But you will be able to actually build things on top and build your local generation agent directly through this Web GPU backend in here. Okay. So that's the overall opportunities that we're enabling on deploying the language models everywhere. And we have made some progress, and more recently, there are a lot more effort focusing on supporting multiple GPUs, making the compilation a bit more reusable so we can target a broader set of models, as well as supporting things like batching for more efficient serving use cases as well. Okay, so I will conclude my talk here, and here's some information I will go through. So if you're interested in learning more about MLC-LLMs, there's the website llm.mlc.ai. We also have open course about machine learning compilation, mlc.ai, that you can go and check it out. Given it's MLC seminar, I also want to give a bit of shout out to the Machine Learning System Conference, which is coming up in the coming year, in the coming summertime, early summer, late springtime. And it's going to be in Santa Clara this year. So, definitely, I think it's relevant to a lot of folks here It's a conference about latest researches in the area of machine learning systems. So definitely you are more than welcome to check it out and try to submit papers next year and come into the conference in the incoming year. Cool. With that, I will be more than happy to answer any questions.
Awesome. Thank you so much. This was super interesting, and it was really interesting to hear about all the specific details about the various design decisions. So we have a bunch of questions that start off with actually some of the TVM logic and design decisions, as well as a few questions about kind of the broader trends around ML compilation, trends around where you see edge hardware in the next few years, and given the sort of massive improvements in the last year and being able to deploy multi-billion scale models on personal devices, where do you kind of see this direction of research going in the future? And so, yeah, we'll start off with some of the more low-level questions around TVM. So one of them was, what are some of the examples of how you reason over blocks, the sort of abstraction that you mentioned for the tensor operations and for the tensor programs, and how do you rearrange these blocks, and what are the sort of optimizations that are possible using this block abstraction?
Yeah, so usually in terms of blocks, right, what we do is we capture the read-write dependencies. So each of our blocks may read and write through regions of tensors, right, and help us to be able to rearrange the computations. For example, sometimes usually you want your data to be local to your compute, right? So you can, for example, inline your computations when possible and reduce the round trip to global memories. Another thing that blocks is very helpful is mapping to the tensor instructions, because a lot of the low-level hardware that we have in the GPUs, you don't simply write a multiply, right? You have to make use of what they call MMA and these like bulk operations. And that's the case. That's also the reason why we design blocks, because we want to be able to map regions of computations onto those specialized hardware primitives there.
Got it. I want to ask a question about kind of overall how you think about building these, large software systems, especially with respect to adoption. That, there's that joke that like, when you have a bunch of standards and you try to build a new one to unify all the existing standards, all you do is like make the problem worse, right? And so I'm curious how you think about those sorts of problems and how you make sure that what you're building is something that people actually want to use and not just kind of create bloat in the software ecosystem.
That is a great question. So I think the first thing that we want to make sure is we do want to enable interoperability in some sense, right? So for example, in this particular case, at least in the TVM Unity, our goal is we want to be able to do Python first development and universal deployment. So we don't have an opinion, for example, you have to use a certain language for deploying the things, right? We want to be able to bring the deployment onto a language that users are interested in. Another thing is that certainly looking at interoperabilities among the ecosystem as well. For example, most of the tensor computations we had kind of conform to this standard called DLPAC that allows you to do things like zero overhead exchange with existing tensor infrastructure like PyTorch and so on. So effectively, you can try to combine that as a piece of larger software ecosystem out there. Yeah.
On a related note, so you've been building the system for a long time. What was sort of the MVP, and what were some of the decisions that you made very early on that you might have had to backtrack on or created a new kind of, would rearrange in terms of how you went to building this?
So I think one of the biggest lessons we learned throughout the building the ML compilation framework TVM especially is that initially we saw that we can try to build a fixed pipeline that solve all the problems out there, but very soon we realized it's hard. Like it's a bit too ambitious, and usually sometimes compilation do not capture all the properties. Sometimes you need to leverage libraries, and new demands comes in, right? So for example, you will need to support. Like last year, people are talking about you want to support convolution very fast, but this year people talk about how do you support quantized matrix vector multiplication very fast, for example. So that's motivated us to think about not only how do you develop the feature that we need, but how do you enable infrastructure so that you can accelerate the development of the features we need. And that is the key motivation behind the Unity abstraction, so that you will be able to have different pipelines even for each machine learning scenarios, as well as being able to swap out, right? Quickly try out different libraries and different development strategies to get to your goal. Yeah.
A couple of quick student questions. One student asks, what do you think the ultimate balance will be between ML systems automatically optimized via compiler versus the hand-tuned and customized optimizations?
That is a great question. And I think the goal here is actually not drawing a hard line there, right? So usually what we observe is that, we want to be able to enable abstraction that allows you to both leverage library and code gen. And then usually that bound shift. For example, as you start to look at possible new hardware optimization, sometimes you find, I really want to try that library because that gives you, that's a bottleneck. You want to go and optimize that. So you're swapping libraries by one line, right? You dispatch the library, you leverage the rest of compilation flow, but then sometimes your compilation flow catch up, right? It discovers new patterns and at some point getting as good as libraries, and you want to be able to swap it out. So the goal here is not trying to have a fixed boundary there, but be able to build abstraction so that you can change this boundary very quickly. Yeah.
And one more student question. For the phone-based implementations, one student asked, are the LLM models stored directly in the phone, or are you making sort of repeated calls to some more centralized storage unit where the student is worried about the cost of downloading a large model on every user's device?
In all the cases that we show so far, the models are stored on the device. Of course, for example, in the browser case, you will need to download the weight once, right, from the internet to your browser cache, but then all the things are stored locally. Yeah.
So new hardware is continuously coming out. So one other question that we have one question that Ben actually had was, how do you anticipate changes in edge hardware in the next few years? But also, as we see new GPU types, how do you see the trend going in terms of what you're now building and sort of anticipating those future changes? And one of the audience questions was, are all of the composable transformations hardware agnostic? So at a high level, we're seeing some new trends in hardware, both on edge and sort of the major GPU providers. And how are you adjusting your process?
So the first of all, right, definitely not all the processes are hardware agnostic, right? You do want to make hardware specific optimizations. But the goal is that you want to make your pipeline flexible so that you will be able to compose hardware agnostic ones and hardware specific ones in a very organic way, right? Instead of trying to push all the things to like hardware libraries in this case. And in terms of anticipating the possible changes in hardware, first of all, we do start to see that memory is becoming more interesting, right? So you will see definitely I would anticipate that the hardware is going to have more focus on memory bandwidth and memory size in general. Because we are kind of at Anders Moore's law, so post-Moore era, so you definitely need to have more specialized computations, either specialized data type, specialized hardware engines for matrix multipliers or quantized matrix multipliers and so on, and specialized data loaders, right, to improve your memory loading bandwidth. But that would mean that programming model is going to be more tricky, right, than the current programming model you have. So that's where having abstractions like block that might be helpful to help you to be able to do some of the remappings more organically, but also having a composable pipeline is helpful because you don't want to really build for the current hardware and then new hardware comes, you need to spend time re-engineering a lot of things, right? The goal here is that as new hardware backend comes, you will be able to quickly swap some of the hardware dependent ones and quickly try out new ideas on or existing ideas on the new hardware more quickly. Yeah.
And one very quick follow-up question to that from the audience on YouTube. What do you see as the main bottlenecks for sort of these generated kernels matching the performance of hand-tuned CUDA kernels?
That's a great question. So first of all, on some at least for the MLC single batch inference case, we see the generative kernels are matching or outperforming in certain cases hand-tuned CUDA kernels. So the goal is you want to make sure, first of all, your model abstraction can capture possible things that CUDA can write, right? So for things like batched use cases, there are still certain gaps, but for other use cases, we can go and match the existing CUDA generative kernel, and it's an active research process, right? That's why you want to be able to enable both libraries as well as the generative kernel, so that you will be able to make best use of both of them. Another thing is that you certainly want to make use of generative kernels, especially for some of the compute intensive tasks, because in those cases we can do a lot more operator fusions and automate code generation. So in all the cases we are leveraging, for example, in the CUDA case right now, for a single batch inference, we are generating all the matrix vector kernels and all the other kernels, but we are using Catalyst for actually attention only. And that is because we didn't spend a lot of time optimizing attention. So this scenario can also change in the future. Yep.
But one more question from a student. For large models specifically, like for, I think, language models presumably, what cases do you see edge computing being sort of the better case versus centralized data center compute? What's the trade-off space? When would you prefer each?
I think it depends on what we mean by edge, right? For example, this computer I'm using right now is like the latest M2 Max laptop, and I can run 17 million models without any problem, right? So edge is getting pretty beefy depending on what you mean. Like for mobile devices, certainly you have to run smaller models. So I think the space is big enough that there are opportunities for exploring both. Certainly, I think centralized based server is still going to be very useful because it's very convenient, right? It also allows you to create endpoints that you can interact with it. So I think it's useful to think about both approaches and think about how you can enable a system that explore both approaches as well. Yeah.
One more low-level question is, we're interested a little bit in some of the compilation aspects you needed in order to handle weight quantization. You mentioned this has definitely been something people are very interested in this year. What support did you add in?
That's a great question. So the goal here is you want to build a generic pipeline that handles quantized weight, right? And in there, actually, for matrix vector kernels, for example, we do like a memory access pattern analyze. And then you write the loops to make sure that things are tied and packed in a correct fashion, so that you can generate efficient quantized kernels. Yeah, and I don't have a bit more details on that, but in general, it's about analyzing loop patterns and trying to bring in better locality. Yeah.
Well, as a follow-up question on that, have you had any thoughts about or trouble with sort of getting determinism to behave well with these compilation pipelines? Like in particular, I'm thinking that often there's different heuristics for matrix multiplies of different sizes on different hardware that can lead to slightly different numeric results. I guess I'm curious if any of your users have been concerned about this or if this has ever been a problem.
I would say this problem already happens on PyTorch and other frameworks already, given that, for example, CODN is already non-deterministic. We are facing a bigger problem right now because, we are trying to do extreme quantization. Like FP16 right now is kind of like a good in certain cases. So I think one trick is that you do want to try to make sure that certain values have the right data type, right? For example, if you are accumulating your softmax scores across very long contexts, you want to use 32-bit floating point because FP16 sometimes overflow. So if you are being very careful with that, I find that usually it's okay. But I think it's also because we are kind of trying to push the extreme region right now, and we are talking about usually like 4-bit as opposed to like 16-bit. Yeah.
We'll wrap up shortly. Last question is, beyond sort of ML compilation, what kinds of other topics in machine learning systems are you particularly excited about and focused on your students?
Yeah, so I think one answer there is check out MLSys conference, right? The MLSys conference have a lot of exciting things on this area. They have, to name a few, the techniques are how do you do scaling up machine learning models, right? Certainly very interesting. And I think that's also relates to compilation as well, in a sense, how you can bring the abstractions so that you can represent the parallel programs across chips and so on. There are also questions about, how you're able to, bringing in better edge computing support, right? And doing better model compressions, algorithm support for executing those models efficiently. I think, as of today, like, it's much more clear that you will need to really have a joint machine learning perspective and system perspective for a lot of those problems, right? And I know that a lot of us also have been, submitting papers, doing research on different venues and so on, and definitely, checking out MLSys conference and submit papers to there. It's a great venue to getting connected with folks and learn all those related techniques as well. Yeah.
And touching on that, there are new architectures being proposed continuously. And I know our lab, for instance, really enjoys thinking about alternate architectures to attention, for instance. You did mention during the talk that you might want to have a more efficient attention implementation. There's some support for this. To what degree are the optimizations in your system built around certain popular architectures that already exist, like primarily attention, I guess, versus kind of new bespoke architectures that people might be playing around with?
I think that's where ML compilation can shine, right? Because a lot of cases, the optimization are more reusable. For example, the MLC-LLM do have support recently for RWKV model. This is like a variant of the linear recurrent neural net models, right? And they had it running on from Android, and it seems to be pretty good. So like, I do believe like the ability to be able to support broader range of models is a very important question. And in this case, having a ML compilation pipeline that allows you to have generic optimization mixed with specific optimization to bring you to pass that product milestone, right? Something that can help bringing those models, like for example, RWKV on browser and other environments. Yeah.
All right. Well, thank you so much. Thank you to the audience for joining us today. You can subscribe MLSys Seminar YouTube, and we also have a mailing list for future speakers. We'll see you next week, where we'll have Dan Fu, a PhD student with Chris Ray. He's also here with us today. Awesome. Thank you so much again, and see you all soon.
See you.